Hello all, and welcome. Thank you for coming to tonight's lecture. It's my pleasure to introduce this week's distinguished speaker, Dr. Jessica Larsen. I came to UAF in 2016, actually to pursue my PhD with Jess. In the meantime, I have successfully finished the degree and get to continue working with Jess in a more collegial setting. It has been a real honor and pleasure to work with Jess during that time. I've gotten to experience many wonderful things here at UAF and the Geophysical Institute thanks to Jess. Jess started at UAF in 1997 as a faculty member for the Department of Geosciences here at UAF. And in the meantime, she has advised countless graduate and undergraduate students. She is currently the Associate Director of the Geophysical Institute, and a lot of her research is done in our local experimental petrology lab, which she manages, where Jess grows her own magma in the lab in a controlled setting to understand how magma is stored in the lower crust underneath active volcanic systems, which she's going to talk some more about today. During Jess's time here at UAF, she's worked very closely with the Alaska Volcano Observatory as one of their head geology researchers with the Geophysical Institute's division of the Alaska Volcano Observatory. So without any further ado, I would like to introduce Jess, and she has moved her sites from the Aleutians more inland to active volcanic systems in interior Alaska, which she's going to talk about tonight. So thank you.
Thanks, Nate. I've got. Thank you so much, Nate. Really appreciate that. Really nice introduction. Well, I'm really glad you all joined me tonight here to talk a little bit about one of Alaska's most mysterious volcanoes, Mount Churchill, which you'll see during the course of this talk is actually pretty hard to get to. So we know very little about it geologically. So with this talk, I'm going to share with you some the scope and some really preliminary results from a project I have going on right now with many wonderful students that's supported by the National Science Foundation. So I just wanted to really thank NSF for the funding that's supporting this work. So, let's see. There we go. It's a little slow, but that's okay. All right, so as Nate said, I arrived in Fairbanks in 1997, and to my great excitement, it was because I wanted to start working on volcanoes. I got my degree as a geologist and then did a little excursion into deep mantle studies of water in the Earth's mantle, and then really wanted to get back up onto the surface of the Earth. So when I arrived in Alaska, I feel really fortunate. My career has allowed me to work on volcanoes from the Aleutian Islands. On the left, there's a photo of me out at Okmok Volcano on a beautiful sunny day in the Aleutians, which does happen. Here's valid proof. Not always, but sometimes it's like that out there. And then I spent many years out at Okmok, produced a geologic map with some amazing colleagues with the AVO and the State Geological Survey and USGS. And on the right, more recently, I was working out on the Alaska Peninsula with AVO, looking at Pavlov Volcano. And I put this photo in there to show we were looking at so many ash layers in the peat bog that we used refrigerator magnet letters to keep track of them, because there were like 26 of them, and it was really hard to keep track just by notes. So this is a great method developed by some of my AVO colleagues for keeping track of those tephras. The tephra is a word basically that in this context of this talk is just going to mean volcanic ash. Okay, so we are really fortunate in Alaska. We have a lot of volcanoes. On this map image, I show a bunch of red dots, and those represent some of the more than 100 volcanoes that we have in the state that have been active within the past 10,000 years. More recently than that, we have approximately 54 that have been active within the past, say, 250 years. We call them historically active. We have lots and lots of volcanic activity, which is one of the reasons why AVO exists, of course, because our volcanoes are so frequently active that we really need to keep track of them so that we don't have issues with ash aircraft encounters and ashfall downwind interrupting people in their communities. The reason why we have volcanoes is because you have the Pacific plate. This is one of these big lithospheric plates that the outermost layers of the Earth is made of. They move relative to one another, and in our region of the globe, the Pacific plate is diving down underneath the North American plate to the east, and then a more recently recognized plate called the Bering Plate out towards the Aleutian Islands. And when you have that subduction process happening, you generate big earthquakes, and you also generate a lot of volcanoes along that subduction zone. It's called a volcanic arc. We have another interesting subduction zone where in the eastern part of Alaska, you have this also somewhat newly recognized plate called the Yakutat microplate, which is outlined in this hatchered red region here, and it's actually being sort of pushed along by the Pacific plate, and it's also subducting underneath the North American plate. But it's a really weird subduction situation, and I'll talk about that in a few slides. And so that's why we have the Wrangell volcanoes and Mount Churchill, which I've shown here in this little red triangle. So I have to talk about volcanic ash hazards in Alaska. Volcanic ash is our primary hazard. We have an average 1 to 3 ash-producing eruptions per year, and that's an eruption that is, significantly hazardous, so that, aviation has to be warned. We will get, pretty frequent ash fall on communities downwind. I've got this map up here, which shows in the sort of blue and green outlined areas and the little red area for Pavlov, some of the ash fall distribution maps from some of our more active volcanoes in Cook Inlet, that's Redoubt and Augustine, and in the Alaska Peninsula area, that's Pavlov. The prevailing winds blow typically from the west to east or sort of southwest to northeast. So you can see that when the Cook Inlet volcanoes erupt, they produce a lot of ashfall in the Anchorage area pretty much all the time. So Kenai to Anchorage, our most populated parts of the state, typically get fairly frequent ashfall from the Cook Inlet volcanoes. Churchill, I've put up there too in the sort of southeastern corner where it lives in the Wrangell Saint Elias National Park. The red dashed lines there show the outlines of 2 of the lobes of the Mount Churchill eruptions in the past 2,000 years that I'll talk about today. And I just put those up there just to show that if we had a Churchill eruption in the future, interior Alaska communities and definitely parts of Canada would probably have significant ashfall. So ashfall is a major hazard. You don't want to breathe it. You need to clean it up. If it falls on an airport, you have to clean it up. They close the airport until all the ash is gone because it's so dangerous for the aircraft. Heavy ashfall can really damage your roof. It's bad for your car filter. So when we have ashfall incidents like this, it really kind of impacts our lives. You have to stop and clean it up. And then, of course, the other hazard is aviation. I pulled this out of Flight Radar 24. It's just sort of a screenshot of an average time period where you see all the jet traffic. Kind of in the North Pacific region, you'll see there's an arcing line of jets that kind of goes from sort of the west coast of the US, arcing up towards the Aleutians and then back down again. Those are the NOPAC routes. They connect North America to Asia. There's a variety of other polar routes that aren't quite as well expressed in this time snapshot. But you can just see how much air traffic there is these days. There's a lot. So 60,000 people per day on international flight routes, the NOPAC flight routes that we're showing here. That's a lot of people. That's a decent sized city every day. So ash clouds, even before the ash falls out, are a really big hazard to aviation. So we really care about this. And the AVO is really, really good at monitoring and forecasting and detecting eruption ash clouds that keep all of these people safe from ash aviation incidents, like what happened in the 1989 eruption of Redoubt. Churchill is the little red triangle again, and you can see it's right in the thick of things with aviation. Churchill eruption in the future would cause major impacts downwind. It would impact international air traffic. It would impact us in Fairbanks and Anchorage, and it could impact ash. The ash could impact aviation concerns for thousands of miles downwind. So it doesn't matter that it's a remote volcano by Alaska standards or by global standards. Ash aviation hazards are really a worldwide issue. It doesn't matter how remote your volcano is. All right, let's zoom in on Churchill. So Mount Churchill is located in the Wrangell-Saint Elias National Park. It's in really the sort of southeastern corner of mainland Alaska, as you can see on this nice map from AVO, from the State Geological Survey branch of AVO. It is more than 15,000 feet tall, 4,766 meters in elevation. It's the tallest volcano in Alaska. That's tall. I mean, to do geology on a mountain that big is like a serious mountaineering expedition. So you can imagine not many geological field trips have happened to that volcano. There have been some, but they've been very, very rare. So it's really remote and it's very difficult to access. And this is why it remains unmonitored by the Alaska Volcano Observatory. It's classified as a high threat volcano, which means that there should be some monitoring around it. But in Alaska, we have these real problems with remote volcanoes. They're just really hard to study. And this is probably the hardest, the most difficult of them all. Okay, so I'm going to dive into a little bit of plate tectonic stuff here, and I don't want you to be intimidated by this map. I'll walk through it. It's quite an interesting region of our state. This is an unusual tectonic location for a volcano in Alaska. Most of our volcanoes are along the primary sort of Alaska Aleutian subduction zone that I showed you on a prior slide, where all the red dots were arcing out along the Aleutian Island chain. That's kind of normal subduction in my opinion. It's just, Pacific Plate goes down into the mantle underneath North America and the Bering Plate, and you get partial melting in the mantle and you create magma. Here's a little weird. So the Yakutat microplate is this buoyant sliver of lithospheric plate that is outlined here in this diagram. Let's see if I can get my laser pointer to go right here. So it's diving up underneath North America along this Hatchard curve. And the Hatchard curve here, or lines here, that marks out sort of the projection of where that plate is underneath the North American plate as it's going down into the mantle. It's sort of what geophysicists have been able to image of where that slab actually is underneath North America. So it extends kind of far up into the interior. Jumbo Dome and Buzzard Creek Mars on the north side of the Alaska Range are kind of on the very north edge of where people think that plate is. Collision in this area between the Yakutat microplate as it's trying to subduct its way underneath North America and the North American plate creates some of the most rapidly uplifting mountains in the world. So the Saint Elias Range, which is right down in this corner here along the coast. Oops, my laser pointer's not really, it's jumping around too much. So you can see it's kind of right where the 50 millimeter per year arrow is. So the Wrangell, in this map, they call it the Wrangell Arc. It's denoted in red there. That's where what I like to think of it as the Wrangell volcanic field is. There's really big volcanoes there. Mount Wrangell, it's a giant shield volcano, 900 cubic kilometers. It's just, or 900, yeah. It's just a humongous shield volcano. It's one of the biggest volcanoes by volume in Alaska. Mount Churchill, tallest volcano in Alaska. There's another series of older volcanoes in this area as well. So these volcanoes, you can see they occur kind of in this weird region. They're off to the eastern edge of where we think the Yakutat microplate is kind of underneath North America. And then it's also between that and where some of these really big, they're like giant transform faults are, like the Denali fault. These are faults that go all the way through the crust. They're giant, they're sort of an extension of this transform plate boundary that's south of the Yakutat microplate along southeast Alaska down into Canada. And so those big faults kind of arc up and around. And so the Wrangell volcanic field is kind of in between where this Yakutat microplate is and where these big crustal scale faults are to the northeast. So if we could actually kind of peel away and get a cross-section down into the mantle about what's happening in this area, this is a really nice figure from a paper, and there's a lot going on in this figure, but I'll just point out some of the key things that to pay attention to, why we think that Mount Churchill exists, basically. So on the top, you've got the map view, and then on the side of this is sort of like if you were to cut away and look underneath the North American continent there. You can see there's overriding plate up here. That's North America. And then you'll see this subducting oceanic plateau or crust coming down in here. That's the Yakutat microplate. When this subduction happens, you drag a bunch of water down into the mantle of the Earth. And that comes from the ocean. You've got serpentinite minerals in here. They've got a lot of water in them. When the water gets down into the mantle, it basically you release the water up into the mantle wedge from the slab, and it creates partial melting in the mantle. It lowers the melting point of the mantle rocks. And so that melt then can percolate up into the overriding crust, and it pools as magma chambers, and it feeds volcanoes. So that's probably the main reason why Mount Churchill is there, is because of the subduction process of the Yakutat microplate. Okay, I've actually got sort of a, there we go, right in here. Okay, so here's a map of the volcanoes in that area. It's actually really amazing. It's a beautiful, beautiful region. There's actually a volcano you can drive to on the Nebezna Road and go hiking. It's Skookum Creek. It's up here in the sort of upper reaches. Oops, the squirrely laser pointer. Okay, maybe we'll stop using it. It's a little too squirrely. You can see it up there. It's sort of in the north side of the Wrangell volcanic field, Skookum Creek. It's on the very end of the Nebezna Road. So if you're interested in a nice little summer hike out the Nebezna Road, you can go hike up and see Skookum Creek volcano. It's a few million years old, so it's old. Mount Wrangell and Mount Churchill, you can see I've put red triangles there for them. They're on sort of the southern side of the Wrangell volcanic field, and there's this 100-kilometer dashed line that goes through this map between Mount Wrangell and Jarvis, near Mount Drum and Blackburn, and then Mount Churchill and Bona. That is the depth in the mantle where that Yakutat microplate is reaching 100 kilometers. And that's sort of a magic depth for subduction zone volcanoes. That's the depth when the slab that's underneath diving down into the earth releases all its water, and that's what causes that partial melting in the mantle to create the magma. So you can see Mount Churchill and Mount Wrangell, those are the two youngest of the Wrangell volcanic field volcanoes. They're along that 100-kilometer depth line. So that's why they're there, is because of that melting process in the mantle. Mount Wrangell is historically active. It last had a small eruption in the early 1900s. And Mount Churchill, as you'll see coming up, has had two of the largest explosive eruptions in North America in the past 2,000 years. So it's also very young. So yeah, the extreme elevation and remoteness make this a very challenging volcano to study and monitor. Some folks from AVO, Game McJimsey, and some other scientists from a couple universities in the US were able to go visit the volcano in the early 2000s. They had a helicopter. They did also climb up to the summit region. On the left, you can see there's a person walking up a slope. That's not snow. That's like a giant pumice mound. So that's like really, really thick explosive eruption deposits up in the Klutlan Glacier area that they were able to access. And on the right, here's a rare picture of the summit of Mount Churchill. You can see there's sort of a flat plateau, and then there's a peak on the left, and then a little bit of peaks in the background. That is probably the crater where these really explosive eruptions came from. You can see it's just covered in snow and ice. There's not a lot of rock exposure, so there's not a lot for the geologists to really look at, even if you can get up there. Okay, so I'm going to segue now, and we're going to talk about the White River ash eruptions. So these are at least two of the largest, most explosive eruptions from a North American volcano in the last 2,000 years. I say at least two because the stratigraphy is still being worked out by people who are, these are huge areas that this ash deposits are covering. So it takes a while to work out sort of the time record of what Mount Churchill did in this region. So I've shown on this map a few things. One, the little green houses with flags on it, those are towns. You can see Fairbanks, Delta Junction, Eagle Chicken, Dawson, Haines Junction, Whitehorse. So all of the towns in the region that are either within where these deposits landed or nearby. You can see the two little border guard symbols. Those are our border crossings. The southern one is Beaver Creek. It's a main border crossing on the Alaska Highway. The northern one is Little Gold Creek on the top of the World Highway. So I wanted to put this up here to show you the North Lobe, 1,900 years old, the East Lobe, 1,150 years old, and then these two little Lena tephras down in southeast Alaska, 300 years old. Those are all from Mount Churchill. The Lena tephra still has kind of a question mark about it, but most likely it is a Churchill eruption, and it's 300 years old, so it's very young. So these eruptions, they're young. They covered a huge area in ash, huge area. I mean, this goes across the Yukon into the Northwest Territories, northern British Columbia, and then the North Lobe goes up and covers Tok, Chicken, Eagle in that region. So these are huge eruptions. And Mount Churchill may be as young as 300 years old. So that's very young. So that's why we care about Mount Churchill. I'm actually going to back up a little bit. I just wanted to sort of note a couple things here. One is Mount Churchill is dormant right now. So while I'm talking about these giant ash deposits, I don't want you to get too alarmed. It's just nothing's going on there that we know of. Even though it's unmonitored, we usually see some signs, even at these remote volcanoes, that they're becoming restless. And it's quiet right now. It's dormant. So the work we're doing mostly is to try to figure out where the magmas are stored in the crust that produce these eruptions with now, while it's quiet, so we can come up with some models that'll help us understand seismic unrest in the future if the volcano becomes restless. But the other thing I want to impress upon people here is not just the aviation hazards to ash, which if Churchill erupts again at this magnitude would be really, really serious for us here in Alaska, but also, we've got thick deposits along the Alaska Highway. There's thick deposits on the Klondike Highway, and there's thick deposits on the Alaska Highway on the Alaska side from the border towards Tok, as well as up the Taylor Highway towards Chicken and Eagle. So this is an interior Alaska volcano, really, if you think about the impacts. The road system would be largely cut off if we had eruptions of this magnitude in the future. So it's a serious concern. Okay, so part of this project, which is really fun, is I taught a summer field course this last summer, and then part of that course, the students also came back to Fairbanks and learned how to make magma in the lab. So they got to go learn how to do, measure ash deposits in the field and measure their thicknesses and look at the characteristics of the ash and come up with what we call an isopack map, which is just a map like the one I just showed you where it shows the thicknesses of the layers of ash as you get further away from the volcano. But they also got to come back to the lab and cook magma, which we'll talk about in the latter part of this talk. So I've taught a few field courses, and I did an experimental petrology course this last fall with some of my undergraduate and graduate students. Yeah, we just had a really good time. So these are just a selection of photos from the field trip on the left and then the experimental part in the middle and the right. So during this summer school, we traveled very far. It was an 8-day trip, and we drove from Fairbanks to the Taylor Highway, and we drove up the Taylor Highway and looked at North Lobe deposits, where you see the little pins in the Google Earth map image. The swooping sort of oval lines in here, those are the isopacks from these two eruptions. So what I mean by an isopack is just these areas of equal ash thickness. And when you have a big eruption, you have a big ash cloud, the thicknesses of the deposit go from really thick right near the volcano to thinner and thinner and thinner the farther away you go. And if you map all of these thickness layers out, you can actually estimate the volume of the eruption. You can get sort of a magnitude to compare to other eruptions. So the road system here makes for a really great course where we can chase the deposits and the students learn how to measure the ash thicknesses and describe the samples in the field and take good field notes, and then put all of these thickness measurements together to see how the north lobe changes when you go further away from the volcano, or the east lobe. How thick is it on the Alaska Highway versus on the Klondike Highway? So these pins show basically going up the Taylor Highway towards the top of the world, and then we crossed at Little Gold Creek, a really beautiful border crossing that's like super up there in the mountains, and it's really remote and beautiful. And then we came back down through Dawson and the Klondike Highway towards Whitehorse. So those are the pins on the right side of the map in the east lobe. And then we swung back around again through Kluane Lake area and measured deposits up along the Alaska Highway, and then made our way back to Fairbanks through Tok. So 8 days, lots of ash, lots of stops. And I want to share with people that, you know, if you're driving this way down the Alaska Highway from Tok towards the border, you'll see white stripes in the road cuts. Keep your eyes out for them. There are a lot of pullouts there that, you know, you can just pull off and take a look at those deposits if you want. They're really, really visible. Yeah, it's pretty fun. Road geology is fun. Yeah. It's a nice break from helicopter work out in the stormy, rainy, foggy Aleutians. It's a real fun time. Okay, so this is just going to be a little quick tour of where we went. So this is a stop with the red circle on the pin on the map on the left. It's on the Taylor Highway south of Chicken. Here, the ash is pretty disturbed. You can see I pointed to where it is. It's these white stripes in the loess, basically, and there's a couple scales on the right. They're reworked here, which just means that the ash layers are laid down nice and even like snow, and then the wind and water and erosion comes and kind of messes them up. But you know, we have probably 2 to 7 centimeters of ash there. It's pretty prominent, and you know, you can see on the map scale on the left, we're pretty far away from Churchill. It just shows how big that eruption was. We swung up around and went across the border at Little Gold Creek, and this is on the top of the World Highway. It's east of Dawson in the Yukon. It's really pretty up there. Red circle around that pin shows where we are in the map. And these deposits were up here. We found them. We had to dig for them a little bit in the little lower right with the finger pointing to the sort of a dark gray streak there. It's kind of hard to see in the photo. But we did find a little bit of ash there, preserved 200 miles north of the volcano. So again, really big explosive eruption will put ash fall really far away. On the Klondike Highway, there's a lot of really, really thick deposits. So the red circle there, we're between Dawson and Whitehorse. And you can see on the lower right, there's like a bunch of white lumpy stuff. That's all White River ash. It's a lot of ash. It's over thickened there because when they built that road grade, they had to kind of scoop the dirt up to make a nice level road platform and then the ditch on the side. So it's a little over thickened there, but you can just see just how much ash there is on the Klondike Highway. It's a lot. I mean, it's like 30 centimeters or like almost a foot of compacted ash. So that's huge. I mean, on the Klondike Highway, Mount Churchill could really, really seriously like close that highway for a long period of time if it had another eruption of this magnitude in the future. So these are some pretty eye-opening things to see on our interior and Yukon highways there. All right, swinging around again towards the south. Now we're at the Lakeview area. This is between Kluane and the border, Beaver Creek. On the left, you can see some of the coarser grained White River ash east lobe deposits. The grain size is a little coarser here because we're closer to the volcano. And they're really thick. I mean, it's like 1/2 meter of volcanic ash deposits on that Alaska Highway between Kluane and the Beaver Creek border. That's a major artery. It's a major international border crossing. It's a major artery into and out of Alaska. And we've got, you know, 1,150-year-old 1/2 meter thick ash deposits on that highway. beautiful spot with a little stream. We had a good time there. Yeah, this fun trip. Okay, so back into the North Lobe. Now we're east of Tok on the Alaska Highway back in Alaska. We pulled out, this is just sort of a quarry area you can see on the upper right. You'll see a prominent white stripe on that upper right photo. That's the White River ash deposits. And then the lower left, it's sort of scraped away a little bit more, and you can see there it's kind of finer grained. But still we have 3 to 5 centimeters of ash in this area east of Tok, between Tok and the border on the Alaska Highway. And so just with this tour, I wanted to show you just how widespread these ash deposits are and just what some of these outcrops look like. This is all in road cuts. So, you know, we just basically mapped it all out by taking a few preliminary trips, and then during the summer, you find a place where it's really easy and safe to pull out, and you can work in the road cut there, and the ash is really, really visible. Okay. Part 3. So, what we really want to get out of this work is where are the magmas stored beneath Mount Churchill? Or at least where were they stored during the 1150-year-old White River ash East Lobe eruption? So we're going to take a couple of different methods to figure this out. Okay. On the left side, we can use the natural mineral crystals in the volcanic rocks, and those can give some pressure and depth estimates. So I'm showing a little crystal there. There's a little scale bar that's 100 microns. You'll see that's a plagioclase crystal, and you'll see all these bubbly things in there. Those are called melt inclusions. And a melt inclusion, as I'll get to on the next slide, can provide a lot of information about what the melt composition of the magma was, as well as how much water and carbon dioxide, these explosive gases, that magma had in it. And on the right is a really hot, glowing pressure vessel where we pressure cook magmas in the lab, which is also a very interesting type of research, and it's also pretty fun. There we go. Okay. Okay, so we use mineral melt inclusions to figure out magma storage depths as sort of a guess ahead of time. And these are pretty good, but the error bar on them is really large. So we have a plagioclase crystal there. It's a crystal that grew in the Mount Churchill magma when it was sitting in the crust before the volcano erupted. And these minerals, when they're crystallizing, they have holes in them, and they'll trap little blobs of melt inside the crystal, and they'll trap gases along with that melt. And so then the volcano erupts and the crystal comes out and it cools and it preserves a little bit of quenched melt in those melt inclusions. And those melt inclusions, the little bubbles in them, they also contain volcanic gases like water and CO2. And these are a primary tool that we use to try to figure out how much volatiles, water and carbon dioxide, the magma had in it, how gas rich it was, and you can use that to figure out what depth the magma came from as kind of an initial guess, because the amount of water that you can put into a melt that comes from a magma increases with pressure. So the more water you have in that melt inclusion, the higher pressure it was when that crystal formed. Okay, so how do we pressure cook magma in the lab? So I got a little recipe here, and we're gonna go through it. First, you crush up a piece of Mount Churchill volcanic rock. Then you add about 10% water. You put it in a really high pressure, temperature resistant metal container and seal it up really tight. You pressurize it to 500 to greater than 1,000 atmospheres of pressure. So this is like 500 to 2,000 bars. You heat it up to temperatures of 1,200 to 2,000 Fahrenheit, or about 700 to 1,100 degrees Celsius. You let it cook for a week or longer. It's really important. You don't want to pull it out too soon, because then it's like half baked. Okay, and then you cool it off by dunking it in a bucket of water. And I've got a video coming up that'll show you that. All right, so step one, we crushed up some Mount Churchill volcanic rock that was collected from the Klutlan Glacier by Gay McJimsey of the Alaska Volcano Observatory, and I show you the sample on the right. It's a really nice piece of big pumice from the volcano. You just take a mortar and pestle and you grind it up really fine and get a nice little crushed up volcanic rock. And then I have this wonderful diagram. This was made by Ed Bloom. He's an UAF undergraduate student who did some of this research with me and my grad students in a class this last fall. So you take a little metal capsule, that's A. You seal up one end, which is B. You weld it closed on the bottom. You add a little bit of water, which is step C. Then you add some rock powder, the crushed up Mount Churchill powder on top of that. That's step D. Then for E, you have to kind of squeeze down over the powder in the middle of the capsule, because you want to add what we call a buffer capsule assembly, which is basically just an oxygen sensor like you have in your car. We want to make sure the oxygen partial pressure in that little capsule magma chamber is about what it was in the volcano. So we have to do a little chemistry there. So we make a separate little capsule that sets that oxygen partial pressure, and we put that in the top, and then you weld the top closed, and then you've got your tiny little magma chamber. So here's a couple of pictures of Mia Yanis. She was a Columbia University student who came with us on the trip this summer and had a really good time. And she's right there welding with a jeweler's torch, making up the little tiny magma chamber using a silver capsule, welding both ends of the tube after you put the rock powder and water in. On the right, this is what one of those tiny little silver magma chambers looks like with Erica Rader's hand for scale. Erica was a former master student of mine a while ago. So that's your little magma chamber. And then on the left, you can see there's sort of a kind of greenish looking rod. That is a pressure vessel. It's made of a super alloy called waspaloy, which is a nickel-based super steel that can withstand really high pressures and temperatures. So we need those super steels in order to simulate the crust of the earth at really high pressures when we put it in the furnace. So the attachment nut, that goes to the pressure line. So you put that little silver capsule inside of that pressure vessel, and then you put it in a furnace box. So you can see the vessel on the left sitting in a furnace box that's not hot. So we're just loading that one in there. And then on the right, you can see when we heat that furnace up, it heats the pressure vessel, which is at high pressure and now high temperature, and so that's how we cook the magma. And these are simulating crustal pressures and temperatures that a magma might be at underneath Mount Churchill. When we're done, after cooking for a week or more, the pressure vessel's taken out and quenched quickly in air and water. And these are some fun photos that Florian Hoffman, a GI faculty member who came into the lab to watch us quench during this class, took with a little infrared camera that he had. So you can see all of the light regions are hot and the purple and blues are cold. And you can see that there's on the left, we're getting ready to take it out. In the middle, there's a student with the hot pressure vessel, which is glowing really white hot. And then on the right, they're dunking it in the bucket of water to cool it off. Okay, and so hopefully this video will work. Okay, so what we're going to do is we're going to, we have the high temperature furnace here. So Claire is in the audience. You will see Claire in a moment quenching this experiment. And we have this tube coming in, and inside of it is a pressure vessel, and that's like the crust of the earth at high pressures. And inside of that is one of those tiny little magma chambers in the silver capsule that I showed you in one of the photos on one of the slides in this presentation. So you'll notice we wear a lot of PPE because we're working with a high pressure line as well as really hot vessel. So we wear welding jackets and face shields, and we use safety shielding in the lab when these experiments are running. And that's in there, and right now it is at really high pressures and really high temperatures, temperatures of, let's see, more than 1,500 Fahrenheit. And so Claire is gonna take the vessel out of the furnace and quench it off so that we can retrieve the little synthetic volcanic rock that we've created for making magma. Okay, what Claire's going to do is get some compressed air. We blow the red hot glowing pressure vessel off with the compressed air first, and then she's going to quench it by dunking it in a bucket of water. You want to step back so you can see the glowing red hot vessel. All right, and then when ready. So I think this one was at 850 C, 850 Celsius. And this one was at 1,500 bars, which is equivalent to about 6 kilometers depth in the Earth's crust. Then we have the Folgers coffee can, which has valiantly served the lab for more than 20 years. I just realized when we made this video, like, oh man, that coffee can, that has been like a successful tool in so much published research. I can't even tell you. It's a critical component. All right, that looks good. Okay, now we have a cooled off little tiny sample of volcanic rock that we created in the lab inside of that cooled pressure vessel. This is experimental petrology for you. It's a little bit of a, yes, experimental petrology. It's a really interesting field of research. We make a lot of our parts. Actually, I saw Dale in the audience. Dale can be thanked for many of the things in the lab that you see here that work really well to make this research possible. So we need local machine shop. We do a lot of our own building of tools and instruments because we have to. These are not commercial things. They're really specialized. Okay, so once you've quenched your experiment, you have a capsule on the right, it's all peeled apart. You pull out your tiny little piece of synthetic volcanic rock, which is shown there in the little vials. You put it on a glass slide, you glue it down, you grind it and polish it, and then you put this carbon coat on it on the right so that we can look at it using an instrument we have here called the electron microprobe. And Nate Graham, who introduced me as the manager of the Advanced Instrumentation Lab here, and basically, the electron microprobe is like a super duper scanning electron microscope, but it also allows you to pinpoint spots on your sample really precisely to analyze the composition of whatever mineral or the glass in high precision and accuracy. So you get this beautiful scanning electron view of your sample, and then you can narrow down to pick spots in your sample that you want to know all of the chemical information of that mineral phase or the glass. It's a wonderful instrument, and actually this makes the research possible. Without this instrument, we couldn't do these types of experiments here because we wouldn't get the information we needed out of them. So we're really lucky to have the AIL here. So on the right, you can see Abby Naston. She's with the State Geological Survey, and Mia on the right. They're learning how to use this microprobe to analyze the results of the experiments they created this summer. On the left, I'm showing these, we call them backscattered electron images. It's just like a scanning electron picture of what you see in your sample. On the top, I've got a hornblende crystal. It's also called amphibole. Beautiful little diamond-shaped thing that grew during the experiment. And then on the bottom, plagioclase, also grown during the experiment. So the point here is to do a bunch of experiments at a bunch of different pressures and temperatures, and then in each one, you see what you grew. Did you grow all the minerals you find in the Mount Churchill natural rock sample? Was it all glass because it was a really hot experiment? Or what combination of minerals are you finding? And you have to map all of that out, because the goal here is we want to recreate that natural rock sample at controlled pressures and temperatures So then we know the pressures and temperatures that made that rock. So you might be wondering, why are we simply remelting the rock? Like, what does that actually tell us? So we start with natural sample constraints. I'm showing a few different pictures here. The left is magnetite and ilmenite on the bottom. Those are crystals that can tell you something about the temperature of the magma based just on their chemistry. They grow at specific temperatures, and you can measure them, and then you can model what those temperatures were. In the middle, I'm showing the melt inclusion picture again. Those melt inclusions at Mount Churchill, so far my master's student Ozzy is finding at least 5 weight% water in these little melt inclusions, which means that they probably formed around 5 kilometers depth below the volcano, but the depth range is really uncertain. And the temperature range from those magnetite and ilmenite grains is also really uncertain, big error bars. So we want to know things much more precisely than what they tell us. On the right, we have the natural rock, which has 85% glass, 10% plagioclase, 4% hornblende, and 1% of this magnetite and ilmenite. So when we do the experiments, that's what we want to recreate right there. We want to surf around in pressure and temperature space and create all these experiments so that we can basically say, aha, at these pressures and temperatures, that's exactly the mix of glass and minerals we have. So we start with the melt inclusions. They give us the green bar. That's sort of the pressure range. You can see it's really broad and wide. We start with the magnetite and ilmenite. They give us this orange range in temperature there. It's also really broad and wide. So I made a map here with pressure on the Y, on the vertical axis there, from 0 to 2,000 bars, or 0 kilometers to 8 kilometers depth in the crust. And then on the Y-axis, we have temperature from 600 Celsius to 1,000 Celsius, just to give you an idea of the range that we're looking in. So what we're aiming for is something like that blue box up there. It's much more precise. We have experiments that are recreating the natural rock in a narrow set of pressures and temperatures, and that's what we're aiming for. And we go through this whole pressure and temperature space, and we map it out by doing experiments all over in this range. Lots of experiments. I haven't shown the dots here, but you can imagine little dots at various pressures and temperatures that are searching around until we can finally recreate what the natural rock had. At really high temperatures, we have a lab-created rock that's all glass or melt, and we know that's not right because we know what Mount Churchill has in it. So we know it's not up there. On the lower pressure side, we have a lab-created rock that has glass and plagioclase and some pyroxene, which isn't in the natural sample at all, but we don't have hornblende. So we know that's not right because we know that the Mount Churchill natural rock has hornblende in it. So we know it's not down there. So in this sort of overlapping region where the melt inclusions are and the temperature from the minerals are, that's a really good bet. And that's where we're doing our current experiments right now. And when we finally recreate in that range a sample that has 85% glass and 10% plagioclase and hornblende and all the right proportions, then we know the pressure and temperature range that magma formed. And it's a much more narrow pressure and temperature range than we get from the melt inclusions alone or the mineral temperature estimates alone. We've really narrowed it down a lot more. So that's why we bother with all of these experiments. And then we come up with a magma system plumbing model. Here's a cartoon drafted by my master's student, Ozzy Schneider, who's working on the melt inclusion part of this program. You can see a cutaway. There's Mount Churchill, and there's a magma chamber down there, the red with the X's in it. You can see a scale bar on the side, 3 to 9 kilometers depth. The melt inclusions are telling us that magma is at least 5 kilometers or deeper beneath Mount Churchill summit, but we don't really know. That's really preliminary data, and it could be a big depth range we get from those melt inclusions. The experiments are in progress. We need a lot more at higher pressures, so we haven't quite figured that range out yet, but we're getting closer. And so why do we even do this? So we know we get earthquake activities beneath volcanoes before they erupt. The experiments are going to give us an a priori model for where that activity might happen. If we know the magma is stored between 5 and 7 kilometers depth beneath Mount Churchill, and we suddenly have a bunch of earthquakes in that region underneath Mount Churchill, we might be able to say, wow, that might be actually magma. It's not just tectonic earthquakes or a fault or anything like that. It might actually be magma. So that's why we create these plumbing system models, is to try to give us a look ahead of time where we might expect earthquakes if the volcano is becoming restless. And early warning like this, it just helps us be a lot better prepared for when the volcano becomes restless, and we'll have a much better idea of what that seismic activity means. If it's magmatic, we can help get prepared in case Mount Churchill might erupt. Okay, so just a summary. I've got a lot of text up here, but I just wanted to kind of circle back. Alaska, we have more than 100 Holocene volcanoes, 54 active in the recent past. And Mount Churchill is this mysterious, high elevation, high threat volcano, tallest volcano. It's really remote. It's unmonitored because it's so hard to even work around there. It's hard to, you can't even fly a helicopter. It's too high elevation. So it's not directly monitored by the Volcano Observatory. And we need to learn more about this volcano because it's produced at least 2 of the most explosive eruptions in North America in the past 2,000 years. So thick ash deposits along major highways and roads in Alaska and Canada. You can imagine air traffic disruptions, thousands of miles downwind. So it's a serious volcano. So we need to know more about it. And we're trying to figure out where the magmas were stored in the crust beneath Mount Churchill so that we can create a plumbing system model in case of future unrest. We'll be a little bit more prepared. We'll be like, okay, it's probably 5 to 7 kilometers depth, and then if an earthquake swarm happens in that location in the crust right underneath the volcano, we can say, maybe that is magma. Maybe we need to really start looking at this volcano. Our preliminary results suggest that we've got at least 5 kilometers or deeper of magma storage at Mount Churchill, but we have a lot more work to do to figure it out in more precise depth estimates. And then we can use this model. We'll know a lot more about the volcano. It'll help us prepare for a future Churchill eruption. Okay, and with that, thank you. It's very hard to actually see Mount Churchill from anywhere where you find these ash deposits. So Ozzy took this photo of not Mount Churchill because you see the products, but not the volcano.
All right, thank you, Jess, and thank you for your graciousness in dealing with the technological issues. I actually really loved your off-the-cuff narration during the silent video, so thank you for that. So we'll take some questions from the in-person audience. I have a microphone I can run on this side, and one of our students, Chloe, has a microphone on the other side. So raise your hand and I'll bring you a mic.
Thank you very much. So my question has 2 parts. So the first part is regarding eruption types. Geologic history, the word Vesuvian eruption comes from observations of Mount Vesuvius erupting in AD 79. And you can correct me if I'm wrong, but Surtsey, is that how you pronounce it?
Yeah. Mm-hmm.
The one in Iceland?
Yes.
Erupted in 1963. That type comes from observations of Surtsey erupting. And then, there's Hawaiian type eruptions for, well, you guessed it, seeing Hawaiian volcanoes erupt. So my question, I guess, how do we classify volcano eruption types, and what type of eruptions does Mount Churchill display, I guess, if that makes sense?
No, that's actually a really, really, really great question. So I showed on previous slides how we have these big regions of ash deposition downwind from the volcano. I called them isopachs. They're these big sort of oval-shaped regions around which we draw for equal thickness of the ash deposits as it gets thinner, as you get further away from the volcano. So eruption classifications for explosive eruptions are determined based on basically how much area we call them isopachs, those isopachs cover, as well as the grain size that you find of the ash in those isopachs. So Mount Churchill, actually, these eruptions would have been classified as Plinian. So like what Pliny the Younger saw with Vesuvius 79 AD. That was sort of, that's where that term comes from. So these are really long duration, just a fire hose of ash and gas coming out of the volcano, going to really high altitudes, like 50,000 feet would be even low for something like this. So really, really high altitudes. And the ash travels really far downwind. So the pattern of its deposition on the ground, as well as the grain size at specific distances, is how we use that to come up with that eruption classification. I don't know if that answers your question. Yeah. So Mount Churchill, these I would say at least Plinian, maybe ultra-Plinian. That's a kind of a weird one. It's like a super big Plinian eruption. Maybe the East Lobe would have classified as that. Yeah, but certainly Plinian. Yep. So like Vesuvius.
Just curious to know how much experimentation went into the magma recipe. I don't suppose that's something you can just Google and come up with.
Yeah, you could, but yeah, it's a lot of experimentation. I mean, it's kind of an interesting field because these methods for looking at making magma have been around for a while. They've been around, gosh, I'm trying to think. I don't know, for people in here who've ever had like a Geology 101 class, if they remember Bowen's reaction series, where you look at the temperature of minerals crystallizing, and as you get cooler, you get different minerals crystallizing starting from one whole magma. Those experiments were like in the early 1900s. And I think, I'm just trying to think back, because I think people like Bowen who started these, they probably were just like, oh yeah, we could just build like a big pressure cooker and like cook the magma in there and watch it crystallize and quench it and then figure out what we formed. And then they get more and more sophisticated. You add like the oxygen partial pressure, and you add, specific other things to your capsule to do, very, specific types of experiments. But the basic method has been around for a while. And it's really pretty simple. And I kind of like that. And we can't like completely recreate a magma chamber because, it's a tiny little capsule and we can only put so much in it and we can only have so much pressure and temperature control. But the method we've been following here has been around for probably 30 plus years. So we're basically just sort of doing what other people have done that we know works really well, and then just using that method on different volcanoes to try to learn more about volcanoes that we've never explored before.
My question is on the duration of the eruptions. So your best guess for like the depth of some of those layers, how long might that have taken to do that? Is it like a nova erupta, very short, high power kind of fire hose, like you said, or is this maybe 6 months, a couple of years kind of thing?
Yeah, that is a really, really good question. So an individual explosive eruption event, like what would have created some of these ash deposits, could have been anywhere from maybe like 12 hours to 48 hours in duration of just continuous ash coming out of the vent. Vesuvius 79 AD was 24 hours long from start to finish, which is kind of amazing. You think about it, it seems like a short amount of time and it did so much damage, so much devastation. Where it gets tricky with something like this is we don't know yet if, say, that big East Lobe was one event that lasted maybe, I don't know, it could have been a couple days or maybe even longer, or if it was, like 12 hours and it stopped, and then another 12 hours a couple months later and then it stopped. There's just not a lot of that record preserved. So we don't know if it was one big eruption or multiple smaller eruptions that happened in a succession of time over, maybe a year or two. Just don't really know. The longest duration of these explosive events that I know of was the Bishop Tuff eruption in Long Valley in California. And I think there were some estimates that one went on for about 5 days. That's the longest one I know. sort of in a continuous eruption.
One more question from in person. All right.
Yeah, I'm going to try to tie this into an earlier presentation in this series, but back in the very early 80s, I was in the Seattle area and managed to witness the Mount St. Helens eruption. And I know prior to that, as it was building towards its final explosion, there was a lot of photography and video being done, from different points on the ground and showed deformations and stuff like that. Earlier in this series, we had a presentation on remote sensing. Is there any sort of effort being made in a study of Mount Churchill that involves that, like overflights, aerial imaging to look at ground deformations or stresses?
So the best way to do that probably would be from the NISAR satellite or one of the synthetic aperture radar satellites. Those are really great at picking up volcano deformation. So that would be amazing if we saw a signal like that from Mount Churchill. However, the complication there is it's covered with snow and ice, and that makes that sort of geophysical monitoring from satellites a little bit more difficult because the information you get bouncing off the ground is bouncing off sort of an unstable substrate of different depths and everything, and it just really, it doesn't usually work out all that well. So yes, if the volcano becomes restless, people are going to be looking at the synthetic aperture radar data to see if there is some ground deformation with magma coming in and swelling the volcano. But I feel a little hopeless that we're going to get a really good model from that. So with Mount Churchill, probably the best bet is the regional seismic network operated by the Alaska Earthquake Center, which it's not as dense as like a volcano monitoring network. We usually put instruments right around the volcano so that we get really good, you can capture even little small earthquakes. I've been reassured by Mike West, the state seismologist, that if Mount Churchill became restless, if it's creating bigger earthquakes, it would probably get picked up on the regional network. So I think that's probably the first place we would see unrest. Unless, say, someone from Alaska Airlines jet saw steam coming out of the top of the mountain, which would be a great, great thing to, alert us to what was going on. Yeah.
Okay, lots of great in-room questions, and Jess is happy to chat with you after we go through our online questions as well if you have more. So we have 109 folks on Zoom. Carl Benson, who is one of our Geophysical Institute Emeritus, is on, calling from Raven Landing in Fairbanks. We also have Judy and Bob, two of our sponsors, calling from Oregon and Fairbanks respectively, Andy in Anchorage, Sharon from Eagle River, Steffens or Stevens from McCarthy, Dennis from Seattle, and Brian from Pennsylvania, and it's after midnight there, so that is a dedicated Science for Alaska person. So just a couple online questions. We have a ton, so I'm sorry if I don't get to yours. But question from Dean on Zoom. Can you explain what a melt inclusion is?
Sure, yeah. Okay, so melt inclusion, if you imagine you have a magma and it's cooling off slowly and you have minerals that are growing in the magma. So as the magma cools off, you'll get mineral crystals that crystallize out and grow. And these crystals don't grow perfectly uniformly. So you might have, it branches out and you've got like a skeletal shape with a lot of holes in it. And then the outsides of it will seal up as the crystal grows and forms sort of like an outer shell around this sort of Swiss cheese in the middle. And inside of the crystal, you are basically trapping little bits of the melt phase from that magma in that Swiss cheese part. And then if the crystal doesn't completely grow, out and the magma, if the magma erupts, then that crystal's flung out and cooled really quickly, and those little pieces of melt are quenched into glass. But they're still included inside of that mineral. So other people call them glass inclusions because really they're glass by that point. But what they're trapping is little bits of melt from the magma chamber. And along with it is water and carbon dioxide and sulfur dioxide and all the gases that were inside of that magma as well. So they're like a treasure trove of information from this tiny little blob of melt trapped in a crystal that we can get out of what the magma actually looked like.
Nice, thank you. Question from Lee on Zoom. Thanks for a great talk. Just curious if why we can expect the magma chamber in a future eruption to form at the same depth as you will have determined it formed in a previous eruption.
Yeah, that's a really good question. And with a volcano like Churchill, that's a little bit hard because we don't have a lot of geology on Mount Churchill. On some of the other volcanoes I've studied, when they've had multiple eruptions, like Augustine Volcano, for example, in Cook Inlet, and they've been observed, and people have studied the past eruption, and then the next eruption, and then the next eruption. When we do an experiment on those volcanoes, we have a pretty good idea that it's been doing the same thing for a while. With Mount Churchill, we're basically using its eruption history, that it's produced similar composition magmas from the North Lobe and the East Lobe and then the Lena tephra to say, okay, we think it produces the same type of magma through time. And so the assumption we're making is those magmas are forming in a spot in the crust that is long-lived and that is persisting in that volcanic system for thousands of years. It's not a terrible assumption, although it is an assumption. So in the future, you know, that's the best guess we have as to where the magma is probably going to park itself again, just because that's probably a place in the crust where magma can pool pretty easily, although we don't know 100% for certain.
Okay, thanks. And one more, again, I apologize to online folks. There's so many good questions. Question from Tom on Zoom. Could this latest eruption have forced indigenous people further south into southwest regions?
It did, yeah. So there's, I'm not an expert on this, so I didn't talk about that today. I didn't really feel like I had enough accurate knowledge to share. But Josh Ruther from the museum here has done some work on this eruption as well with radiocarbon dates. And there's really great evidence that the Dene people living in the region downwind of the volcano at the time migrated out of the area. And there's some, it's my understanding, and so if somebody in here knows more than me, please correct me if I'm wrong, but some people think that that's why the languages are similar between Southwestern indigenous people and the people that were in that area that migrated out after the eruption. It definitely changed a lot of the animal populations and the vegetation. And so, you know, a lot of what these people were subsisting on changed pretty dramatically. So it was a huge impact.
Thanks for answering all those questions. Another round of applause for Jessica.